Hi, folks. The Energy of Life is our Unit 2, Chapter 4. Wonderful content. So the introductory video for today actually, oh, excuse me, I was wrong with the video that it actually was. And so it's a video about, it's old school, it's Mr. Wizard, and it has to do with sugar. So I'm going to pull that up. I'm going to move things over real quick here. And I'm going to pull up and we're just going to watch this video about burning sugar with Mr. Wizard, who's old
Here,
school.
Como, I have a pair of safety glasses for you to put on because you and
thanks.
I are going to do a somewhat dangerous experiment. So it's a good idea to be prepared.
All right.
Okay? First of all, do you know what that chemical is? You know what the C stands for?
Carbon.
Carbon. And the H?
Hydrogen.
And the O?
Oxygen.
Yeah, when you put them all together, like this in this form, you got sugar.
Okay.
Yeah. Have you ever burned sugar?
Yeah.
You know, it has a sort of a typical caramel kind of smell. Well, when you burn sugar, you actually free the hydrogen and the oxygen, so you get water, and what's left behind is the carbon.
Yep.
And you've noticed when you burn something on the stove how black it gets?
Yeah.
Well, let's burn some sugar. I'll put in about a teaspoon or so. Get rid of the lump, okay? Now, here's a nice long stick, and at the end of it is a match.
Mm-hmm.
So you take the match, and I'll light the match on the end, and you put it down there in the sugar, okay?
Okay.
Okay, put it down in there. Doesn't catch on fire, does it?
No.
Why not?
Because
What do you need to have a fire?
you need oxygen.
Oxygen, and usually it comes from air, right?
Yeah.
And that's what happens when you burn sugar on the stove. Well, you don't need air. You really need a supply of oxygen, as you said. And here's where we're going to get it. You know what the K stands for?
No.
Potassium. The N?
Nitrogen.
And O?
Oxygen.
Yes. And it's that bunch of oxygen right there that we're going to release and combine with the carbon in the sugar.
So then it'll catch on fire.
It sure will. Take the teaspoon, put in about a teaspoon or so of that chemical, put it in there with the sugar, and mix it all up. And I'll get rid of these. And notice I have it on a piece of wood here that I use for burning things. Okay, now one of the problems is we have to get it started. So I'm going to put some match heads in the middle. So what you do with the match at the end of the stick is you bring it near those match heads and catch them on fire. So they'll catch the rest of it on fire. And you will soon see that you don't need air for a fire. All you need is a good supply of oxygen. Okay, bring it down there close. And step back over here with your hand. Get ready to stand back. There we go.
That's neat. It's
Yeah.
all bubbling.
Yeah, it looks like a volcano.
Yeah, a miniature
And all
one.
we're really doing is burning sugar with a good supply of oxygen.
It's fizzing now.
So what do you need to have a good fire? Do you need air?
No, you need lots of oxygen.
Right.
All right, folks, so I thought that would be interesting to show all of you because, let me pull up our thing here. That is our introductory kind of video because as we move forward, we are going to be looking at the idea that we need sugar, so some type of sugar source, which is our fuel. We need to have oxygen molecules present. So again, like you said, not the air, but oxygen present. So O2 molecules, or O molecules, right? So we need to have that oxygen present. And we have sometimes need a little bit of accelerator. And what's actually happening when that fire occurred is we're creating energy, we're creating heat energy. And so we're going to see that transformation throughout the next few weeks of how we need that glucose, that sugar. We need to have oxygen, especially in our bodies, to make things work and fuel and energy to occur. However, what I have to say about that is you don't have to eat sugar in order to do that. Your body is amazing, and your body can actually take protein and fats and turn them into sugar. So your body knows how to make sugar from whatever you fuel it with. So don't by any means go and start eating a bunch of sugar that you don't already eat just because you think you need it for fuel. Your body can turn many other things into sugar because it's amazing like that. Now, energy and biology, so again, thinking about living organisms is really important. we need energy for the ability to do work. And our energy is going to be different than other energy sources. So it all kind of starts with these producers. Now, producers are autotrophic, meaning they can make their own food, so they can make their own fuel source, but they need energy to do that. And how they get that from is from solar energy. So that could be from the sun, or it could be some type of light energy that it can use, because we know producers such as plants and aquatic plants and algae and some fungi, not all, basically are producers, and so therefore they need some type of solar, sun energy, light energy to start this process. And when they use that light energy and they use carbon dioxide from the environment, they create their own fuel source, so they create their own glucose. Now we know that us as consumers and then decomposers can't do that. We're all kind of in this category of heterotrophs, meaning that we need other organisms in order to get our fuel. And to get fuel, then we need to make energy. So consumers, we have to basically ingest other types of organisms, whether that's other consumers, or it might be decomposers, or it could be producers. So we, as humans, will eat usually some type of meat source, some type of plant source, but we also might eat some type of fungi, which are decomposers, such as mushrooms. So what we need is that we eat this solar energy, we take it in from another organism. We need the oxygen that the producer got rid of, because we didn't need it, doesn't need that, and we give them CO2 back into the environment. Same thing with decomposers. Decomposers want to take the oxygen in the environment that the producers gave, and it's going to produce CO2. Decomposers need other organisms. They're kind of a spongy organism. They want to grasp onto things and basically absorb all their nutrients. So that is this center here, triangle of kind of life, or circle of life. You may have heard of it before, where we all need each other and we all help each other in order for us to be sustainable, but also for us to produce energy. Energy is here for this little guy. This guy produces things for us and for this. We need that solar energy to make our own energy as we move forward. So organisms are basically considered an open system. That means that energy enters, it usually cycles through somehow, and then leaves the body. So usually we have energy enter the body primarily from what we are eating, from what we are taking in, and it cycles through and gets used, and then it leaves the body primarily as heat. So that might be just temperature leaving your body, or maybe when you're exercising, you're increasing that heat and you're producing more energy. If we were a closed system, energy couldn't enter or leave. So that would be more challenging for our bodies. We would be in a very more stagnant place. So let's just talk about types of energy for a moment. So potential energy, everything has potential energy, whether it's living or non-living. Every little thing has energy. So if you're sitting at your desk or a table, your computer has energy, your pencil, papers, maybe you're sitting on the couch, that has energy, the TV, the remote, whatever you are around, everything has potential energy. Stored energy that will be available to do something once a force is acted upon it. Now, kinetic energy is the energy of motion. So once force is put on an object, it now changes. So once the force is now applied, what happens is whatever that object is usually in motion. And that is what we call kinetic energy. So in my example here, I have an archer. They're holding their bow, and if the bow was just at resting, so maybe they were just holding it here in their left hand and not getting any force upon it, this string actually has potential energy. In its normal state, kind of original position, it has potential energy. The energy is stored. It is not done with until we start to change that. So now our archer grabs the string, pulls it back towards his chin, and we are gaining potential energy now. So not only do we have the potential energy that was just kind of sitting there stagnant, now we have more potential energy. And as soon as he lets go of that string, the arrow is going to leave his hand, leave the bow, and now it's in forward motion. So that was force put upon it. It's gaining kinetic energy, and the energy is flowing as if the arrow was flowing. So we can apply some laws to energy, and these are what we call the laws of thermodynamics. The first law states that conservation of energy. So conservation. So what that means is that energy cannot be destroyed or created. So energy can't be created or destroyed, but it can change. So that it can change what type of energy it is. So we call that conversion or converting. So the other law here is entropy. So again, during this conservation where we're converting the energy, we use a small amount, so we lose a little bit. But again, it's not destroyed. It's still energy. It's still moving. It just changes. And so we are a little bit at a loss for this. So energy transformations happen often. So when we look at different types of energy, this is nuclear, this is solar, this is chemical. We can have electrical, we can have mechanical, we can have light energy, we can have heat energy. So there's so many different types of energy transformations, and basically if the energy starts nuclear and it transfers to solar, it just continues moving. So it's converting. It is not going away, it's not destroyed, it's not creating, it is just moving along. Like I said, you might have a little entropy where we lose a little bit of energy as it transfers, but it's not destroyed, and that's really important to think about. So metabolism is the total of all the reactions in a cell. So what I want to show you in the next video, I want to show you specifically about Rube Goldberg. Rube Goldberg is a physical way of making a simple task much more complicated by showing you the transfer of energy between one thing to the next. And I think a visual is really important. So I'm going to end this video on metabolism and pick the next video up in the same exact spot.